In this lesson, we shall look at the method of finite differences actually that pertains applied mathematics, right? And we actually consider the boundary value problem, right? Which is d squared y dx squared plus 2xy equals 2, where x lies between 0 and 2 inclusive. Right, set up the set of equations to solve this problem by the method of finite differences when h is what we call delta x. So in other words, the step length, or what we call the step size, h is sometimes called delta x. In this case is 1/2, or as a decimal fraction, it is 0.5. And this particular h, which is the step size, is used in each of the following cases of boundary conditions. You do not have to solve the equations. We shall get a lot of equations, and the examiner is clear that we do not have to solve the equations. So we just need to get the equations and actually stop there. And that is actually the advice here. Now, what we're then looking at becomes the following. So we want to solve this one, and we shall first look at part A, and this is very rich in practice dimensions, and we'll have look at two problems in this case. And we begin by looking at the first one. In other words, part A. We shall also look at part B to practice this a bit more, using different boundary conditions, because you have the following cases of boundary conditions where 0 is 5, where 2 becomes 10. Now, to begin with, we note that to actually solve the boundary value problem, the boundary value problem, d squared y dx squared plus 2xy equals 2, which is the given problem. X itself lies between 0 and 2. So we want to solve the boundary value problem. Why is it called a boundary value problem? Because there are boundary conditions, and these are the boundary conditions. Where 0 is 5, where 2 equals 10. Right, so we continue to analyze this. So to solve the boundary value problem by the method of finite differences, right, so want to solve these by the method of finite differences. There are a couple of things we need to look at, right, by the method of finite differences. We'll look at two things. So first and foremost, we convert, or we change the differential equation to a difference equation. So we actually, we convert the differential equation to a what we call a difference equation, right? Or we convert it into a difference equation, right? And how do we therefore convert this in the differential equation into a difference equation? Because it's method of finite differences, converting a differential equation into what we call a difference equation. How do we do that conversion? Right, and that we need to state the formulas that we actually obviously use in this case. Right. So now I want us to give a brief description of the actual conversion technique that we use. I think that it can always be of great assistance in this case. So we can actually just make things easier. Right, so let us let xi denote denote the grid points. Right, the grid points. And H minus xi plus 1 minus xi, and let yi denote the approximate. The approximate value of y at xi. Let xi denote the grid points. So xi denotes what you call grid points. As we indicated last time, we looked at a rectangular region that has specific points in space, which we called grid points. So the xi's, x1, x2, x3, etc., denote grid points. At this point, the x values lie between 0 and 2. We shall determine how many x values would be obtained in view of the step size delta x equals 2 or h equals rather 1/2. Delta x equals 1/2. So what we then do, we will use the following approximations. So we will use the following approximations. What are the approximations? Well, the approximations we use are as follows. So we look at the fact that we have the second derivative of y with respect to x. So now it means, therefore, we need to note that partial squared y, partial derivative squared with respect to x, evaluated at x equals xi, this becomes approximately, right? So it becomes approximately yi plus 1 minus 2yi. yi minus 1 divided by h squared. Okay, so we note that we have the second derivative of y with respect to x like that. X equals xi. So that now the y evaluated. So we do this, but also we can then say, we also have we put an and here. So the second derivative, which you see here, the d squared y dx squared, obviously it's the total derivative, straight d's, and these are the band d's for the partial derivative, but we use the same relations because the partial derivative is more general and this is just more specific, called the total derivative. But we use the same relation in this module. Or actually in applied mathematics by and large, but this is more general because multivariable functions are differentiated using partial differentiation. But we then say y evaluated at x equals xi becomes yi. What does it mean? It means that y at xi becomes approximately a yi. So that is the notation. So y, whenever evaluated xi, is approximately yi. This, once again, it's an idea for us to actually determine approximations, right, using this particular method. And let's proceed now and look at how we can use these equations to solve. But also, we continue to then say, and of course, x evaluated xi. Okay, and x evaluated xi would be, so in other words, I would have to maybe write here and then say, of course, if you evaluate x at xi according to this method, because we are preparing ourselves to solve the problem. So the formula for the d squared y dx squared is this one. We saw it last time, but we use it again today. And the formula for the y, because we convert everything to method to the to what we call difference equation. So we have to replace the derivative, the second derivative by this. The y will replace by yi. The x will be replaced by xi. And I'll be interested in writing this very clearly to introduce our notation. And we can say, and of course, we say the following. Right. And of course, whenever you have x evaluated at xi, this one can be seen as indeed, can be seen as xi. Right. So in other words, whenever we have an x determined at x equals xi, that we call xi, or x subscript I. Okay. Let's get started with our careful examination of this problem. Right, and because of this, we proceed to then say, thus the differential equation. Right, thus the differential equation, which is what we are supposed to solve, can be approximated. Right, can be approximated at a grid point xi by the difference equation. Okay, so now we can convert this one by the difference equation. So it can be approximated. And we approximate it as follows. So we then say the second derivative can be written as y subscript I plus 1 minus 2 minus 2yi plus yi minus 1 divided by h squared plus 2xiyi equals 2. Right. Right, so we continue with our analysis of this particular problem, and we actually are able to write that representation. And now, if we then say this differential equation, this one, can be written like this using our method of finite differences, but also we've written it now what we call the difference equation with subscripts, converted it from just being what we call a boundary value problem written as a differential equation to a difference equation. And simultaneously, there's certain observations we're making here when we get which is yi. Okay, so when h equals 1/2, we get the following. Let us analyze these together. What happens when h equals 1/2? Okay, we'll perform a small division here of the area. Let's make h equals 1/2 into this equation. And if we do, you shall have yi plus 1, 2yi, right, multiplied through by 4. Well, the 1/2, 2 squared is a 4, but because it is in the denominator, it's 1/4 in the denominator, and therefore it gives us 4 yi plus 1 minus, you can write exactly 8 yi 4 2. Okay. So now in the end, you divide 2. Divide by 2. And if you do, you get a 2 yi plus 1 minus a 4yi plus 2yi minus 1 plus xiyi equals 1. So now at this point, this is what we get. But we can factor out a yi from this one and this one, and would have therefore xi minus 4. We've factored out a yi from this and that. And then what do we have? We have plus a 2 yi plus 1, and the result is 1. So indeed, it is true that whenever h is 1/2 into the difference equation obtained from the differential equation using the method of finite differences, we shall be able to get the equation in blue, but we've rewritten it. We've just established that indeed this is true when h equals delta x equals 1/2 into the difference equation. We're able to write it in this form. Okay. Why is this form preferable? Why was it necessary for us to then say, we have this difference equation, we're writing it in this form? Why? Because we have done grouping of terms here, because the terms were by and large scattered. We had a yi that was in the center, and we had also a yi that was as part of the last term. And so these things were scattered, and we had to perform regrouping. 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 Okay, we'll continue with our analysis. We continue with our analysis. Right, so we continue, please. And we analyze this very carefully. We continue and we take our time to finish off. Okay, so we then have the following. Right, we have exactly the following. We revert to our notion of what we call grid points, established in terms of the x positions in space, and we shall discuss that. So the grid points in this problem, right? So the grid points in this problem or just the grid itself, and we shall elaborate on the notion of the grid. So we note that the grid in this problem consists of, right, the following points. The following points. Now, if then our x runs from 0 to 2, our x0 becomes 0. Remember that now you just add h, which is 1/2, and 1/2 is 0.5. So if x0 is 0, x1, you start from the initial point x0, then you add 0.5, you will have a 0.5. You add a 0.5, you'd have a 1.0. You add a 0.5, you'd have a 1.5. You'd add a 0.5, you'd have 1.5 plus 0.5 is like 2.0. Right. Right. So now we take note of these grid points and we ponder to continue, but we actually need to apply these grid points, the steps we've got. Right. So we continue to analyze this method here. Right. So as we have this in front of us, I want us to ponder on this and analyze the next step. Obviously, we shall write the next step, but there's more reasoning that we need to do here. Right. So we would look at that very cautiously and analyze that together. Okay, right. There's more we need to incorporate. There's certainly more we need to incorporate here. Right. There is certainly more we need to incorporate. Right. There is more we need to incorporate. I would have actually given a note. The note is that whenever we have dy dx, like in the exam, they might put a dy dx there. Like you can see the first derivative is yi plus 1 minus yi minus 1 divided by 2h. But whenever it is the second derivative, we write yi minus 1 minus 2 yi plus yi plus 1 divided by h squared. Right, so, and yeah, we take note of that, and we can say much more on this. But yeah, let us look at the formulas we've written, and together with the note, and continue to solve the problem. Now, obviously, as we are digressing, but also to solve this problem in detail. Okay, let us elaborate on the following. Let us elaborate on the following. Right. The couple of things, obviously, we need to take note of. There's this equation. I want us to give it a name. This one. This equation here, it's very, very important because we worked so hard to achieve it. And what is the name of this equation? We normally give it the name star. star, this one, the equation star. Okay. Now, that equation, then we're going to use it now, and we're going to substitute into it. So now when we refer to star, then we refer to it because there are a couple of equations which I'll write. Now, let us actually make mention of the fact that equation star, right, needs to be applied. Right, it needs to be applied to, or rather at all grid points. At all grid points at which the value of the function y is unknown. Must be applied at all grid points at which the value of the function is unknown. This usually includes all grid points in the interior of the region. But obviously, whether the values of y, right, whether the values of y at the boundaries of the region are known or not depends on the boundary conditions. On the boundary conditions. Okay, we have exactly that. On the boundary conditions. Okay, equation star, that the one we've labeled, which is our difference equation, that's what we call it, needs to be applied at all grid points. We've written the x values at which the value of the function y is unknown. At which the value of the function y is unknown. Like, the value of the function y is known at y equals 0. At 0, y at 0 is 5. But it's also known at 2. Y at 2 is 10. Now, we are then saying the equation star needs to be applied at all grid points at which the value of the function y is unknown. This usually includes all grid points in the interior of the region. But whether the values of y at the boundaries of the region are known or not depends on the boundary conditions. But whether the values of y at the boundaries of the region are known or not depends on the boundary conditions. We have our boundary conditions, and these boundary conditions will be also used to actually solve this problem, in other words. Okay, let us analyze this and see what then we need to do. So in A, we've been given these particular boundary conditions. And so let us see then, but we don't need to solve a set. You do not have to solve the equations. Just get the equations and then off we go. Okay, right. So we focus on the The two boundary conditions in part A, because we shall look at part B very soon, but boundary conditions. Y at 0 is 5. Y at 2 is 10. In this case, okay, when Y at 0 is 5 and then Y at 2 becomes 10. In this case, it means Y at 0 becomes 5. And Y at 4 becomes the 10. Okay, Y at 0 corresponds to X0. But you remember that at this point, our X0 is 0. X1 is 0.5. X1 is this. X2 is 1. X3 is 1.5. X4 is 2.0. Okay, that is why then this X4 corresponds to a Y4. Yet now we don't know the value of Y at what at 0.5, at 1.0, at 1.5, but we know it at 0, and so we know Y is 0, but we also know Y4, which is Y at X4, and that is Y at 2, and Y at 2 becomes 10 exactly. And we continue. We continue. Right. Okay. Right. Okay. Right. So we continue. Right. So we continue, please, y'all. We continue. Okay, now, if we look at these, then we have Y at 4 is 10. We continue with our analysis. Okay, the Y0 is 5 and Y4 is 10 are both known. So we know this. Okay, we know both of them. And therefore, we only need to apply the equation we called star at the interior, grid points, namely x1, x2, and x3. We need to apply star at the interior grid points because now we need to find it at x1, x2, x3, because at x0 we already know it's 5. At x4 we already know it's 10. What about x1, x2, and x3, which are like the interior grid points? Right, 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 right. We continue. We continue. We continue. Right. We continue. We continue. Okay. Now we're dealing with the interior points. As we are pondering on this, we then say that we get the three equations. We get the three equations. So now we remember the equation star. And the equation star actually was just the equation 2 yi minus 1 plus xi minus 4 yi. 2yi plus 1 equals 2. And we called this star, and we recap on it. However, we get three equations more. So it's y0 plus 2y1 equals 2. Right? Okay, so it's going to be, if we put y1, yeah, so it's going to be 1 and then 2 here. Okay, in other words, we're going to make I1 here. If we take I equals 1 here, why do we choose I equals 1? Well, we choose I equals 1 simply because we know that when I is 1, then we're going to get y0, which is our first value, sort of our 0th value, our initial point. Because if we're going to take I equals 0, then it's going to be 0 minus 1. We don't have y at minus 1. We start from x0, which produces or yields y0. And because of that, then we're starting with y0. And therefore, we take I equals 1. When I is 1, 1 minus 1 is 0, 1 here. And then when we take, obviously, our I equals 1, then this is also going to become a 1, right? It's going to become a 1 minus 4, a 1, and then a 2. And then a 2. And then a 2. Okay, what have we done? We, in the first case, have used I equals 1. So we said, effectively, let I be 1 here, which is y0, x1, y1. So now we have this. When I is 1, 1 plus 1, it's 2. I is 1, we have y1, and then we have x1, and then we have the 1 minus 1, 0. Okay, good. We find there. Next. Now we're going to put our I equals 2. Our I equals 2. Our I equals 2. Our I equals 2. So when I equals 2, we have 2 minus 1, which is 1. 2 here. Y2 there. And then obviously we're going to continue to analyze that. And then we have 2y3, and the result is still equal to, okay, yeah. So we need to note that this one is equal to equation star equals 1. Meaning that we're going to have a 1 there. Okay, equation star equals 1. Well, how do we know? Because equation star equals 1. Equation star equals 1. Equals 1. So We use that one. So we put a 1 there, we put a 1 there, we put a 1. Just changing the indices there. Okay, good. Let us continue with our analysis of this difference equation. We've put 2, then we put a 3. And then if you put a 3, you have a 2. Because 3 minus 1 is a 2. X3. 3. 3 plus 1 is a 4. Equals 1. Like this. So now we get 3 equations. And these are the 3 equations. And then we stop here because now we have y0 up to y4. And then y4 is our last one. So we can't continue, for instance, to put, we put a 3 here. Then if you put a 4, it's going to be 3. But then if you put the I plus, if I is 4, then it's going to be a y5. There's no y5 because we have only, as we indicated before, we only go up to y4 because of the grid points. The x values between 0 and 2, there are only 4 of them. In the step length, 1/2, which is 0.5. So we continue. I would like us to continue from the previous analysis. We got 2y0 minus 4. Two y2 equals 1. Minus 4, which is actually y2 plus 2y3. Minus 4. Right, so now, which after substituting the values of x1, x2, x3, y0, and y4 give we have the following. We have the following. Okay, let us substitute everything. So now, if you put y0, like y0 is a 5. So we're going to put a 5 there. And then x1, we know it. Let's substitute it. What is x1? Okay, let's just write the things here on top here, so that we can just remember and avoid a couple of mistakes. Right, so would remember that our x0 becomes 0. x1, you add a 0.5. x2, you get another 0.5, getting a 1.0. x3, add a 0.5, getting a 1.5. x4, you get a 0.5, you add a 0.5, getting a 2.0. So what is x1? Minus 4. What is y1? y1, we don't know it. y2, we also don't know it. We get a 1. Y1 we also don't know its value yet, but we can solve. But yeah, we don't need to solve yet. Need to get the equations. X2 will know. What is X2? It's 1.0 minus 4. Then we have Y2. And then 2. Y3 we don't know. The result is 1. Y2 we also don't know. X3 we know. X3 is 1.5. So we substitute. Minus, yeah, that is X3. Then we subtract 4. Y3 we don't know. Y4 we know. Because from this is a Y0 and then Y4. So we have this. So now, let us simplify everything here. 2 times 5. What is 2 times 5? It's 10. We have 1 minus 10, which is a minus 9. But 0.5 minus 4 is a minus 3.5. Y1 plus double Y2, and it's a minus 9. Okay, now 2Y1. What is 1 minus 4? It's a minus 3. And therefore, this is 2Y1 minus 3Y2, 2Y3, and the result is a 1. And then 2Y2, 1.5 minus 4 is a minus 2.5. And then it becomes 1 minus 2 times 10 is 20. 1 minus 20 is a minus 19. So now this is the answer to this particular question. This is the answer to this particular question. And this answer is in terms of equations. And we have found the equations that are required here to solve this problem. And these equations, because you were supposed to say, and this is the instruction on what needs to be done, set up the set of equations to solve this problem by the method of finite differences. When h is delta x equals 1/2 is used. In each of the following cases of boundary conditions, you do not have to solve the equations. Just set up the equations, but don't solve. Because obviously, you could, this one would be easy to solve. You could actually be in a position to get how many unknowns are there? There's Y1, there's Y2, then there's Y3. Y1, Y2, Y3. So now you just have 3 equations in 3 unknowns, and therefore it actually should be very easy to solve. But we have been advised to actually stay away from solving the equations. And we continue right now to the next one. And we are done with part A of this particular method of finite differences. We continue to the next one, and we look at the method of finite differences next as follows. Right, we move on. We move on. The next one is part B. In part B, the story is different. It's not just y0 that is given like before, it's y prime that's 0. What about if they give you an initial value that is like a derivative? Like the first derivative of the function at y0 is 2, and then y2 is what? Is exactly that one. Now we need to plan our way here. We need to plan our way. But now, because we have been given that the derivative at 0, the first derivative at 0 is 2. Is 2. Then we have the following. Then we have the following. So we first state the boundary conditions. Right, the boundary conditions are different from the former equations. So with this one is 0. Now, y4 is 0, but which is this one, like y4 is 0 because the last one is 0. But y0, what about y0 like before? Y0 is not known in this case. It's not known. And therefore, we need to apply still we have our star in mind at x0 because y0 is not known. And therefore, we need to apply star at x0 as well. As well as at the interior. Grid points. Grid points. X2 and X3. And X3. Since the equation star refers to the value of yi minus 1 at a grid point. At a grid point. Xi minus 1 to the left. To the left of the current. To the left of the current grid point. Xi. To be able to apply star at the grid point x0. We need to also include the value the value for y at xi minus 1, which is minus 0.5. Okay, we're going to analyze what this means. We're going to analyze what this paragraph means. which in essence, which is outside the domain of the differential equation. To handle this problem, we will introduce there's something called a fictitious point once I minus 1 to represent the value y evaluated at minus 0.5. We will write out the set of equations, which is what is wanted. We want to write out the set of equations using this extra point. This extra point, and then use the derivative the derivative boundary value to eliminate it. Okay. We recap on the paragraph we've written, which is a very important paragraph that seeks to iron out a couple of things. We first note that in the part B, because we did part A first, now I look at part B. Part B is a bit different because we actually have an initial value that is the first derivative at y0, and it is 2. So the boundary conditions, y primed at 0 equals 2, y at 0 equals, y at 2 equals 0, because y at 2 equals 0. Now we note that at this point, y4 is what becomes 0 here. But y0 is not known, and therefore we need to apply star. We have got star. We shall just rewrite it again. And x0 as well as at the interior grid points. Right. To get y0, you need to apply y star at x0. And as well as at the interior grid points, because if we have the interior grid points, we then have the result we have. Good. Okay, my goodness. We continue. The interior grid points are, as we said already, like the interior ones, because if you start and say x0 is this one, and then like we saw, x4 is this, and then with x1, x2, x3. They're sort of what we call the interior grid points along this interval, within this interval. And since the equation star refers to the value of y sub I minus 1 at a grid point, x subscript I minus 1 to the left of the current grid point. So if you have xi, the position of xi minus 1, it is to the left of the current grid point. So if you have a grid point, and we're then saying the grid point is xi, then xi minus 1 is to the left in terms of its position. It's to the left in terms of its position. In terms of its position. Okay. To be able to apply star at the grid point x0, we need to also include the value for y at, now we need to, because we need to go to the left. So whenever we're making I0 here, we would get x subscript I minus, x subscript minus 1, yeah? X subscript minus 1. So now that would mean, therefore, if we include that one, and we move the same distance to the left because the step size is delta H equals delta X equals 0.5, like 1/2. And therefore, if you move one step, then you're going to get to minus 0.5. Okay, that is the new development, which is outside the domain of the differential equation. The domain is between 0 and 2. Now, if we go to minus 0.5, then we're going outside of this. To handle this problem, because now there's then a little problem, because now if we go to the negative 0.5, we are going outside the interval, and it is a small challenge because why are we going out? And that raises the question. To handle this problem, we'll introduce a fictitious point. Right, a fictitious point is the y subscript or y sub I minus 1 to represent the value y the value y at minus 0.5. The value y at minus 0.5. We will write out the set of equations using this extra point and then use the derivative boundary value to eliminate it. We will again do what? We will again eliminate it. We'll then use the derivative boundary value to eliminate it. Because it's outside, we will eliminate it also. Okay. We're back now. Now, being back, we then say, what is the equation star? The equation star must be brought back. yi minus 1 plus xi minus 4yi which is this, yeah? Okay, yeah. Okay, if this is our difference equation, if it is our difference equation, is that one? That is what we have. Okay. So this one is star. So now we're going to use our star, but now we're bringing it back to this particular problem here. The application. Right, the application. The application of equation star, which is our difference equation associated with the differential equation, evaluated at x naught, x1, x2, and x3 gives the set of equations. Gives the set of equations When I is 0, and then you have x0, y0. Y1 equals 1. Okay, now we are making I equals 0 in the first one, starting from I equals 0. We have the minus 1 there. We have the minus 1. And then we continue. And then now, what about when I is 1? It's 0. X1 minus 4. Y1. 2y2. So you'd have okay. We've used 1 for I, 2. Y2. And then that becomes 3. Using 2. And then if you use 3, 3 minus 1 is a 2. 3 here. So you'd have x3 minus 4 using I equals 3, y3. Now this one takes us to a y4 equals 1. Let us continue with our analysis of this. 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 Okay, let's check out. So when x0, we said already, x0 becomes what exactly? If we take x0 to be 0, and then x1 is a 0.5, x2 is a 1.0, x3 is 1.5, x4 is 2.0. So we have the following. Then we have the following. So you'd have 2 sub that. And then you'd have if we take x0 to be 0, that's going to be 0 minus 4. And then it's going to deal with y0. We don't know what it is. 2y1 equals 1. What is y0? 2y0 plus x1. X1 is 0.5. 0.5 minus 4. And then we have y1 plus 2y2, and this is 1. Then we're going to go and obtain 2y1 plus x2. It's a 1 minus 4 y2 y3 equals 1. X3 0.5 y3 2y4 equals 1. Now, if you have this here, let us simplify these together. Let us simplify these together. So now at this point, this is going to be, for instance, it's going to be 2y this. 0 minus 4, it's a minus 4y0. 2y1 equals 1, which is 2y0. 0.5 minus 4 is minus 3.5. y1, y2 equals 1. Then you have 2y1. 3.0y2. Which is 2y2. 1.5 minus 4, it's a minus 2.5. y3 plus y4, we already know it's 0. y4 is 0. And the result is a 1. Right, so this is what we've got. And we need to, therefore, simplify this particular equation. And these equations will simplify to the following. If you take these actually exactly into account, you take these equations like this. And we simplify them. Because this one, the bottom one is going to be 2y2 minus 2.5y3 equals 1. Minus 4.0y0. 2y0 minus 3.5 y1 plus 2y2 equals 1. Minus 3.0. 2y3 equals 1. Minus 2.5 y3 equals 1. Right. Right. Okay, we are continuing, please, and we are solving the problem. We're not yet done. Right. Right. We continue, please. Right. We continue. All right. Now, what do we then get out of this? Okay, never mind. We continue. We continue. Right. Right. So now at this point, okay, we continue. Right. In continuing, we are solving this problem. Yeah, obviously. I mean, the equations are visible, but yeah, we continue, please. We have these particular equations. We've solved them. For example, if you look at the bottom equation, 2y2 and then 2 times 0 gives us a 0. You have 2y2 minus 2.5y3 equals a 1. This is it. Right. Next. So what we do next is that next we apply. We apply the boundary condition. The boundary condition, which is exactly 2. This one, because it has been a pain. It has been a troublemaker, but now we are tackling it. So next we apply this boundary condition that is a derivative, because now we remember that this has to do with y's only. The question is, how do we deal with the y that is a derivative in this case? So there's something we call the central differences. So using central differences, using central differences to approximate the derivative. Right, so we're going to use central differences to approximate the derivative y prime at 0. At x0 equals 0. Let us call this one equation 1 from the equation star. All right. Now we note that the equation 1, which is y prime at 0 equals 2, can be expressed. Can be expressed. Can be expressed as the difference. The difference relation. The difference relation. Y1 minus this divided by 2h equals 2. Using central differences to approximate the derivative y prime at x0 equals 0, the first equation can be expressed as this. We have already said that I gave already the formula we use. We said dy dx is actually given Right. Right. So we continue. So you would actually then remember the relation we stated. And there's a relation we stated earlier on. We said this one is yi plus 1 minus yi minus 1 divided by 2h. Like that. 2h. So now if we make I 0 in this, we're able to get y1 minus y subscript minus 1 divided by 2h. So we have that. We have exactly that. We have exactly that. And now when we then say, right, we then say y1, y minus 1 divided by 2h equals 2. Right, with h equals 1/2. You would have divided by 2h equals 2. So you multiply here, and we have the following. Right. So now we have the following. Okay, we continue, please, from this. But you'll be able to see that the 2 times 1/2 becomes a 1, and therefore we have y minus minus y sub minus 1 equals 2. Right, we continue with our analysis of this problem. Obviously, carefully looking at it. Right. Right. We continue. We continue. We continue. Okay, yeah. Taking a deep breath and we move on. Right, moving on. We're dealing with the first derivative is a boundary condition. And we are looking at the skill we need to use. Which is y1 minus 2. Okay, we manipulated. Is this manipulation correct? So if you have the, yeah, if you move the y1, y subscript minus 1 to the right, then you'd have y1 minus 2. So yes, from this, we're able to get this particular equation. And now, if we're able to get that particular equation, let us call this equation, let us call this particular equation double star. Double star. These equations here with the 2y subscript minus 1, call it double star. Right, so we call it double star. Right, we call it double star. So we continue. Right, so, right, you have the following.
Hi, sir. Hello. Sir, I haven't done this module before.
Okay, so we continue. Right, so this is what we have. So we proceed to then say we substitute this into double star. Right, if we substitute into double star,
Yes, sir. So if I had gotten,
so we continue. We continue. Okay, so we substitute these into double star when we got and get this set of equations. Okay, so now this is it. Clever, clever trick. Because we're trying to eliminate these, and we have succeeded in doing that. So what we're going to do is we're going to take these particular equations, all these, we're going to take them forward, and then we shall use this particular formula for dy dx with the subscript -1 to um, eliminate the y subscript -1 in these equations double star. So you'd have the following. You'd have exactly the following. So you have 2y -1 minus 4.0. 2y1 equals 1. 2y0 so you have minus 3.0, which is 2y2 minus 2.5 y3. Okay, let us check. So now, this is the equation we are supposed to deal with. And if you're dealing with 2, what is, okay, we can write a little bit more. Writing out this equation first and then doing algebraic manipulations, like 2 subscript that minus 4.0 y0 plus 2y1 equals 1. And then we substitute what is y subscript minus 1 is y1 minus 2. So we're going to put here y1 minus 2 minus 4.0 y0 2y1 equals 1. And then we're going to have, if we multiply everything here, we're going to have what? We're going to have 2, yeah, we're going to have, for example, there is minus 4y0. Can just write it down. minus 4y0, which is minus 4.0y0. Can write it as minus 4y0. Then you have 2y1 plus 2y1, giving us a 4y1. And then you have minus 4 plus 1, giving us a 5. The next one is going to be this one, 2y0. Plus 2y2 equals 1. Okay, then we have this plus 2y3 equals 1. Minus 2.5. y3 equals 1. Okay, so the equations then that we shall get are these ones. And then you would have this set of equations. And then this set of equations, how many unknowns are there? There's a y0, there is a y1. There are 1, 2, 3, 4 of these equations. And then these equations are 4, but there's a y0, there's a y1. Y0 is 1 unknown. Second unknown is y1. Third unknown is y2. Fourth unknown is y3. So these are 4 equations in 4 unknowns, and we can just use matrices to solve this. But they said, please, you do not have to solve the equations, so you leave them in the desired form. Okay, so something that, okay, we have indulged ourselves. And now this has been fun dealing with the method of finite differences. It was our second time looking at the problem on the method of finite differences. So we need now to continue. We need now to continue. We need to continue and deal with this more in detail. Right. Okay, we shall actually just continue just now. And a couple of things we shall do, but yeah, because we have lots of things to discuss. And now, actually having lots and lots of things to discuss presents us with a lot of opportunities that we can learn and that we can sort of begin to master. And so this is a perfect opportunity for us to learn more, right, on this particular method of finite differences. So I've just concluded this one. We're moving to another method now. Right, we're moving to another method. And so moving to another method would have exactly the following. You would have exactly the following. Right, right, right. Okay, 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 okay. Right, let's continue. Right. So now, if we have this, what is the next question? Right, we look at the next question. Okay, we look at the next one. Never mind. We look at the next one. Okay, yeah, because we have discussed this method of finite differences a bit at length. It will be very important for us to look at a wide range of methods, but try to consolidate and understand more the methods we've learned, which will come in the final exam, rain or shine. This will feature in the final exam. So we have another question which is not going to take us very long. Okay, it's different from the one we looked at last time on the predictor corrector formulas of the what you call the Adams-Moulton method. Right, and so we have, for instance, yn plus 1, which is the predictor corrector. Predictor corrector. And the corrector is this. Predictor is that. Okay. Now I want us to analyze this very carefully and note that, like, in this question, apply the Adams-Moulton method to calculate the approximate value of y at 1.8 and at 1.0 from the differential equation y primed equals t plus y. I said these questions are from like past exams, right? And they're starting values. So now you need to use 3 decimal digits with the rounding at each step. So it's very important that these questions, you write them down and you learn them and you repeat, 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 repeat. So if this is t plus y equals, so you write, the way to learn this is to write the question down and to write down the answer. Try to make sense of the answer. That is how one can learn of this. It's not that the questions will always be very different. They will follow exactly along these lines here. So the given starting values, right? So the given starting values are n equals 1, n equals 2, n equals 3, n equals 4, T1 is 0.0, T2 is 0.2, T3 is 0.4, T4 is 0.6. Okay. So if n, we start normally according to this, we can start because it's 0, 0.2, 0.4, 0.6. So we can start from n equals 1, which is T1, which is 0.0. Then n equals 2, 0.2. N equals 3 is 0.4. N equals 4 is the it's 0.6. Good. Yeah, we can start like that. Then we'd have the corresponding y's, for example. So you'd have like a y1, 2, 3, 4. Not 0.95. That is the first one corresponding to T1 equals 0. Then there is 0.68. Then there is 0.55. Then there is a 0.30. Right, and then we'll deal with the next one, which is the F values, because we know that F of Ty is going to be, yeah, we've written it here. So F of Ty is actually T plus Y, which is Y primed. So we're going to use that one, but also we're going to deal with F1, which is 0.95. F2 is, okay, we add them up. We add them up. So F1 is going to be 0.95, but it is 0.95 because it is T1 plus Y1. And then there is F2, which is 0.88. T2 Y2. F3, 0.95. T3 Y3. F4. F4 is 0.9. But how do we get 0.9 for F4? How do we get the F values in the Adams-Moulton method? We use their differential equation, because the differential equation says F of T and Y, it's given in the exam, which is 2 plus T plus Y. So you add the t and the y. You add the t and the y to get the f values. And obviously, it depends. It's not that it's always that you need to add them up. But in this case, the equation says y prime is t plus y. But it can be 2t plus or 2t minus y, in which case you'll have to substitute into the differential equation and get the values of the f, which is just the output values of the differential equation. Okay, now we then say here it's a 0.9. So, which is 0.9, but it's T4Y4. So what is T4Y4? It's 0.9. So we continue now and check this out. So if we continue like this, then we then say it t equals 0.8. The predictor is, okay, this is the predictor. So the predictor is this one, and this one is the corrector. So to practice, because we are practicing here, the predictor is yn plus 1, which is yn plus h on 24, 55, fn minus 1, fn minus 2, plus 720 x1. So now we then have, let's deal with y. Okay, because this is y1, y2, y3, y4, then we're going to do y5. And then if you do y5, n is what? N is 4, giving us a y4 plus the h. The h, you see the difference is 0.2, 0.2, because if you look at 0.4, then you add 0.2 to get 0.6. So our h is 0.2, we divide by 24. Obviously, this one, Adam's Moulton, is something you know very well. And right, you have, for instance, if this one, I want us to write this following formula first, so that everything can be clear. Because if we make n equals 4, 4 plus 1 gives us a 5. So n is 4, it's F4, 59, F3, F2, F1, and so on. Which is Y5. Which is 0.2 divided by 24. So you have actually 0.9. Right. So we continue. 0.9 minus the following. Right. Okay, we continue, please, yeah? We continue, please, yeah? Okay, yeah, we are solving this problem, Adams Moulton. I know that this one you are familiar with it. You have seen it already, but we're just we're just practicing with this one quickly. Okay, so predictor corrector formulas, and then the next thing we're gonna discuss it will be the two corrections. because we need to discuss the method of two corrections. I'll tell you why you need to discuss the method of two corrections. Sometimes it features in the assessments. So now here we're doing one correction, but sometimes we do two corrections. So we're going to discuss that. So it's 55 at 0.9, and then there is 0.95 for F3. 37, your F2 is 0.88. We have seen that one. F1 is 0.95. So that Y5 is 0.4455. F5 is 1.2455. Okay. Right. Right, 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 right. So now, if we get our Y5 to be actually out of this, use a calculator, we get 0.4455. Then what would our F5 be? We need to know that our F5, according to this, it's going to be T5 Y5. So you take the Y5, which is this one, you get from adding everything with a calculator, right? So you need to be able to use a calculator. This is very important. And then you use the calculator to add. Can I just demonstrate that? Okay, you don't need computer programs in the exam. Okay, so that is the thing that some students will be like, okay, but now how do I do this? Do I need to use softwares? No, no softwares are necessary. You just need to be in a position to do it. Like, let's do 0.3. Just I want to demonstrate that indeed this is correct. Plus, you do like 0.2 divided by 24, and then you open the bracket. 55 times 0.9 minus 59 times 0.95 plus 37 times 0.88 minus 9 times 0.95, and then you close. So it is not 0.4455. So that's what we're getting. And then obviously now you then say you take this one, you add 2. According to this, the first derivative is t plus y. So you're going to add the t and the y. And the t we're getting, as already at this point, it's going to be like a t5. For the y5, it's going to be a t5 y5. T5 it's T1, T2, T3, T4. T5 it's plus 0.2, which is like 0.8. So you're going to add 0.8. Okay, which is 1.2455, which is exactly the F5 there, 1.2455. So, okay, we're moving quickly to practice more. This was just the predictor, and let us to get the corrector quickly. Right, and the corrector is, right, and the corrector is, okay, now we're gonna, okay, the corrector formula for the atoms Moulton you already know is yn plus 1, which is yn h on 24. Then we have 9 fn plus 1, 19 fn, 5 fn minus 1, fn minus 2. And then you have the corrector, but we're doing F5 for the corrector because we did F5 for the predictor, right? Which is the top formula, then the bottom one. So this is exactly Y4, then it's 0.2 of the H, because you can see that H is 0.2, which is the step length, step size, divided by 24, which is 9F5 plus 19F4 minus 5F3, F2. Okay, what is y4? Y4 is actually exactly 0.3 plus 0.2 divided by 24. F5, we've already got that one. We saw it. It was 1.2455. That was F5. F4 is, we saw F4 according to the table we drew earlier. It's 0.9. F3 is 0.95. Now you are dealing with F2, and F2 becomes what we're getting. And let us check out what our F2 becomes. So our F2 is 0.88. Our F2 becomes exactly 0.88. And therefore now it means that you would have a Y5. If you use a calculator, you're going to get 0.5037. And then you would continue to get an F5, and the F5 becomes 1.3037. Why is it the case? Please, as said already, F5 becomes T5 with Y5. Y5 becomes this one we use for the corrector, and then it goes with the T5. As said already, T5 is going to be 0.8. Right, and then we have the 0.8 together with these, and the 0.8 together with these, even if you use a calculator to confirm these. Right, so you would use a calculator and then say 0.5037, you add 0.8. And then you're going to get 1.3037. And that becomes the answer. Okay, right. We shall continue now and look at the next step. So this is what we've done for the, sorry, this was at t equals 0.8. Right, so it was actually exactly at t equals 0.8. Right, so if at t equals 0.8, that is what you're getting, it means therefore at 0.8, y at 0.8. Okay, which is the point. You can use a point, not a comma. So you're going to have exactly a 0.8, and this 0.8 is approximately 0.5037. 0.5037, which is actually exactly 0.5037. Next, we're going to look at the fact that what happens at t equals 1.0. The predictor is which is at 1.0, which is going to be exactly at a y6. So we're going to do, at this point, we're dealing with the predictor, which is the first one, yn plus 1, which is yn, Hn 24, 55, Fn 59, Fn minus 1, 37, Fn minus 2, minus 9, Fn minus 3. Then we're going to do y6. Y6 becomes y5.2 divided by 24, 55. And this is y6 when n is 5. It's going to be f5 minus 59, f4 plus 37. And then we're putting a 5 there, which becomes a 3, and it becomes a 2, which is y6, which is the y5. What exactly becomes the y5? You've got y5 before, and this y5 was the y5 at the corrector. So you'd have exactly the following. So you'd have that y5 for the corrector is a not point, which is the y5 is 0.5037. 0.5037, which is 0.5037 plus 0.2 divided by 24, and you would divide these by exactly 55 times the F5. We got that before, and the F5 became exactly this one, which was exactly 1.3037. The F5 that corresponded with the corrector, 1.3037, 1.3037 minus 59. F4 becomes a 0.9. And then we have 37. The F3 becomes what? Right, becomes, we got F3 in the table, 0.95. We have minus 9. The F2 came from the table. And so we got it to be what? From the table, it became exactly 0.881. Right, using a calculator, you'll be able to get the actual estimate of Y6. So Y6 is 0.8856. F6, 1.8856, which is T6Y6. T6Y6. So the T6, what's gonna be T6? If this one is T1, T2, T3, T4, T5, T6. Okay, so that's what we're getting. That is what we're getting. So that's what we're getting. So yeah, that's what we're getting. This one is for the predictor at 1.0, but we're also going to do the corrector at 1.0 to be able to find the 1.0 estimate. And then we say, and the corrector is the predictor and then the corrector for the Adams Moulton. And then we're able to see that the corrector is the second one, which is yn plus 1. Yn, then we have h out of 24. 9 fn plus 1, then we have 19 fn, 5 fn minus 1 plus fn minus 2 minus 19, which is the order. And we always leave out the order. We leave out the order whenever we are to do substitutions. So we continue with our analysis of this. We leave out the order. Zeta 2. Zeta 2. This is zeta 1, zeta 2. Right. So now this would be a y6 because we already got y5. So the y6 is going to be obtainable at what? It's going to be obtainable at, normally they ask you like two values, like y at 1.8, at 0.8 and also 1.0. So the y6, it's going to be y5, 0.2 divided by 24. So, which is 6. So now we have 6. So now you have actually a F5 here, F4, and then 3. Okay, and this becomes 0. The rest becomes 0. At this point, you would have Y6. What is our Y5? Right, we have already got the Y5, which is actually the same as what here? Right, so we got the Y5, which was actually exactly the same. Here was the Y5. It was not 0.5037. Y5 was 0.5037. And that is what we're going to do. 0.5037 plus, then we do 0.2, we divide by 24, and then we're going to have 9. F6. We've already got our F6. F6 is 1.8856. 1.8856. That's what we plug in here. 1.8856. F5. 1.3037. F4 from the table is 0.9. F3. And then if you do all these here, it's going to be 0.822. 0.822. And therefore this 0.822 means that we have y at 1.0 and y at 1.0 is 0.822, which is the correct value at 1.0. Okay, we have had a fair chance to look at the Adams-Moulton and how this Adams-Moulton method is used by and large in a wide range of problems. Right, and so we continue. Right, we continue. Right, and so obviously looking at this particular method, we've had a fair share of learning the Adams-Moulton method, and also we had the method of finite differences to actually discuss, but we looked at a different dimension to the dimension we looked at last time, because the method we looked at last time was the method of finite differences, but we've had a fair share of interpretation, and I would be actually interested in shedding more light on these particular methods here, and I wish to give more material and more information on this. Right, so at this point, then you need to think deep and attempt to analyze these a bit more in detail and see if we cannot be in a position to get more information at depth. Okay, yeah, I can see the time, but now we want to speak about, there's something I want to say more about the method of finite differences as as we shall conclude our discussion. Right, so now, as we shall conclude, there's more I wish to actually convey as a message of this method. We've solved these particular problems, but we can say much more, even when we need to solve a lot of problems. A lot of problems. So, the question then is, what exactly can we do here to solve a wide range of problems? Okay, I will give more information. I want to give more details. There's some details I want to actually give. There's some sort of a summary I would like to give here that is going to help us to understand these more in detail. Right, right. And make sure that we are able to understand these more at length. Okay, right. We have seen these, but my point is this is not all. This is not all. What more do we give? What more do we give? Right. What more do we give? Okay, right. There's more we're going to give just now, please, before we conclude our discussion. And I want to give it in a slightly more organized manner. So there are some results that I'm sort of processing, and I want to actually share them as we conclude our discussion. Right, that as we conclude this discussion, there's more that we can learn, and there's more that we can know here and be in a position to use, so that our learning can be better and it can be more rewarding. And yeah, there are more patterns we shall learn. Right, there are more patterns we shall learn as we master this module. I want to give more details before we conclude. Right, I want to give more details before we conclude. And I'm going to give the kinds of things that are very popular in these exams. I want to give some little scope on what you need to know. The demarcation to which normally you need to learn the things, because it becomes increasingly important. I know that we are beyond the time, but I want to I want to share these so that it actually can be known and be understood. That when you're confronted with problems, you can know exactly how to do them. This additional info I want to give, this additional information that I want to give, this additional information that I want to give. Right, let us give the additional information here. Okay, right. So now, as we learn these particular methods, the question then becomes, what exactly do we do here, and how do we learn everything we need to learn in this particular module? There are relations we've given, and we can give a lot more relations. And we shall actually give more relations. I wanted to give more, but I can always give more. Okay, let me just give this ones for now. Let me just give these for now. But it's already, there are too many things I wanted to give, but it's okay. Right. There are several things that we need to always remember when it comes to the method of finite differences. What are the things we need to remember? Okay, I've given them, but now let's just write them properly here. Right. So the first thing to need to know is the red one, is the red equation. This one, dy dx, is actually always equal to yn plus 1. That becomes like the difference equation, yn plus 1 minus yn plus 1, but over 2h. dy dx minus divided by 2h. And then now, whenever you have this here, we've already obviously given the formula and said it's yn plus 1 minus. So it's something that you need to note. Okay. Yn minus, or yi minus 1, you divide everything by h squared. And then we learn something else. So in principle, we say that this is when x is computed at x equals xi, can put an equality here. Okay, these are just the formulas that I'm just stating together, so that obviously we use them already today, but you need to just remember them. And then this one is x equals xi, exactly this way. So ordinarily and normally, you actually will learn, you need to be able to remember these particular two formulas, but also when it comes to the method of finite differences, when you evaluate x at xi, okay, you have to so you have yi. Okay, you need to remember these three formulas, because by and large, every paper I've seen centers around this. Okay, you look at the fact that now the d squared, we also stated that at this point we used it as partial squared y, partial x squared, which was approximately that. So obviously we used it for the partial squared in the previous question we did last time. And then here we have the total derivative, and we use it in the same way for the, and these are called like difference equations. And we're able to convert differential equations to difference equations using the method of finite differences and using these particular formulas here. And obviously, I'm sure that, I mean, by and large, this is what you need to remember. It is everything you need to remember to deal with any problem you have that pertains to the method of finite differences. And obviously, I mean, there's more that we want to say, but there are also more problems that you need to solve. And I feel that obviously I was looking at the time already when I paused because if I want to start a new question, these questions are generally very long. Even the next question is very, very long. But I'm sure that we shall look at the next question next time because it's very long as well. But there are too many questions on other chapters as well. Okay, there are too many questions on other chapters like this one. Just to give an example. Okay, the next problem we shall look at is the idea of the second order Runge-Kutta method. Right, so this one we shall spend our time next time looking at the Runge-Kutta methods of different orders. But one order that featured in past exams has been the second order differential equations, where you need to consider the system of coupled second order differential equations with initial conditions. Use the second order Runge-Kutta method with H.2, A23, B 1/3, alpha beta 3 out of 2 to find U prime V prime 8 T equals 0.2. Okay, so this will be our next target. This is our next question, but it's excessively lengthy, very long. So we're going to spend a lot of time discussing this in our next meeting. It's going to be our first example, and then we shall look at other sections as well. Okay, after this, right? But I think that I must thank you for joining us because I can see the time. We are beyond the time. That's why I'm just highlighting these things now. We are beyond the time because if I were to start doing this, it's gonna take us like 20 minutes, 30 minutes, something like that. Okay, so right, but thank you so much. And these questions are ordinarily worth a lot of marks, but I must thank you for joining us. Until we meet next time, I have the program. So we're gonna meet as I conclude. We're gonna meet as I conclude. We're gonna meet on the 27th. In the yup. We're gonna meet on Friday. Yeah, I know, I'm aware of that. Friday. Okay, and today is Wednesday, so we're gonna meet on Friday at 10 a.m. But I must thank you so much for the discussion with you today. Until Friday, 10 a.m. Take care and we keep in touch. Right, and yeah, I'll send
Thank
you
you.
more information. Thank you so much. Okay.
Thank you.
Thank you so
Bye.
much. Yeah, this is recorded. This is recorded, so we shall send the recording. Thanks so much and have a good day and goodbye.
You too. Bye.
Thanks, goodbye.